Hello. In this lesson, we're going to look at how we can calculate electric potential due to a spherical shell of charge. The charge is uniformly distributed. So we are interested in 4 points. So let's say if I take a point outside the shell, let's take this point A, which is really away from the shell, and a point which is just outside the shell. So let's call that point S, and then maybe take a point somewhere inside the shell. Maybe we can call that I, and then the center itself. Okay. So at these 4 points, we want to calculate the potential due to this shell of charge. Now, in calculating potential, okay, so we should all understand that there is meaning associated only with the potential difference. Okay, so what do? We use these known results. We start off with potential energy difference. So the change in potential energy. Okay, so I'll write it in words first. The change in potential energy is equal to negative of work done by, okay, so negative of work done by electrostatic forces. Okay, so negative of work done by electrostatic force. So this is the fundamental equation that we will be using it, and then we should understand that when we look at this change in potential energy, okay, as the work is done by the electrostatic force, uh, the configuration, okay, so the arrangement of the system is changed very very slowly. So what do I mean by that? So if I take a faraway point, let's say it is, this point is at infinity, so I have some point charge here. Okay, so at infinity I have some point charge. Let's assume that we have our test charge, unit positive charge. Okay, so here we have our unit positive charge. So unit positive charge is our test charge. So what is our system? Our system is made up of this point charge, unit positive charge, and the shell of the charge. Okay, so as the distance between these two charges changes, we say the arrangement of the system is getting changed, the configuration is getting changed, and the system's potential energy changes. Okay, now this arrangement is assumed to be changed very slowly when we apply this equation. The change in potential energy is negative of work done by electrostatic force. Obviously, because the arrangement is changed very slowly, as you bring this point charge, let's say, towards the shell of charge, you want to bring it very slowly. So that means as this shell of charge applies an electrostatic force radially outwards, you must apply, okay, an external force which matches the electrostatic force. Okay, so this external force is equal to the electrostatic force. Okay, but we can use either of the forces to calculate the work done, so we're going to use the electrostatic force here. Okay, now if I write this using symbols, okay, so the change in potential energy delta U, okay, is negative of, okay, integral, okay, so work done by electrostatic forces F E dot dr. So we're going to go from some initial position of the point charge to some final position. Okay. Now, because we are interested in calculating electric field and then the electric potential, okay, so we are doing everything per unit positive charge. Okay, for unit positive charge. So if I divide by charge, I should get the change in potential as negative of, wherever you have force we will be using electric field, so E dot dr. So initial position to final position, so this is what we'll be using. Okay, now when we are calculating the integral, we are dealing with vectors inside the integral, right? So for handling the vectors, the dot product, I would suggest take a unit vector that points, let's say, away from the center. Okay, so this is a unit vector r cap, right? And anything that is measured radially outwards is considered positive. Okay, so even though we might bring the point charge towards the center, okay, so we always, let's say, assume that the charge is getting displaced radially outwards. Okay, so it is assumed that the charge gets displaced radially outwards. But when you supply the initial and final position vectors, you would know in which direction the charge is actually moved. But this is a good assumption to keep in mind. It is assumed that the charge moves radially outwards. Moves radially outwards. So keep these two points in mind. So we have a unit vector which is pointing radially outwards from the center, and then we assume that the charge which is getting moved, it has a displacement outwards. Okay, so away from the center, but the initial and final position vectors will actually tell us in which direction it has actually moved. Okay. Okay, so now let's use this expression right here. Okay, so we have this right here to calculate the potential at various points. Okay, and another thing here. So at infinity, okay, so at infinity, the potential energy of the system is considered zero. Okay, and the potential of the system is also considered zero. So that's our reference configuration. That's our reference arrangement. So at infinity, the potential is zero. So the potential due to the shell of charge is zero. Okay. Okay. So first here we're going to take the unit positive charge from infinity to this location A. So somewhere in between. So let's take a point P here, and the distance of this point to P, let's say it is R. Now at this location, the electric field due to the shell of charge, so we can write this down. So as a vector, the electric field is going to be 1 by 4 pi epsilon naught. So we can use shell theorems here. This point is really outside, so we can say it is q by r square. So I'm expressing it in terms of vectors, so I will use that r cap. Okay, and remember the displacement is assumed to be radially outwards. Okay, so the displacement is radially outwards. So let's say we have a displacement dr. So as a vector dr, we will write it as dr is the magnitude and then r cap. So it's assumed radially outwards. So now, so this delta v will be the potential at point A minus the potential at infinity, so V infinity, which we know it is 0, is negative of integral. So okay, so I'm coming from infinity, so let's say I'm going to go till, so this distance is RA. Okay, so the position of A is RA from the center. Okay, so you can imagine a vector from the center till A, which is RA. Now let's do the dot product. Okay, so here r cap dot r cap, it is just 1, so we can leave that out. So 1 by 4 pi epsilon naught q by r square dr. Okay, now VA, and then we are taking this as 0 and as 0, and then negative of 1 by 4 pi epsilon naught is constant, so I'll pull that out. And then what is the integral? So q is also constant, so integral is r to the power minus 2's integral, so it is r to the power minus 1 by minus 1. So we'll end up having minus 1 by r. Now what are the limits? Infinity to Ra. So if I substitute Ra, I'll get 1 over Ra, and then infinity, I think that becomes 0. So what is the potential of this location A? It is simply 1 by 4 pi epsilon naught Q by Ra. Okay, so we are done with this. Now, how do I find the potential at a point just outside S? So if you observe what we have done carefully, all I have to do is, instead of using the position vector for A, I will use the position for S. So that means instead of RA, if I use the distance of S from the center, then I'll get the potential at S. Okay, so the potential at S will simply be 1 by 4 pi epsilon naught Q over R. Okay, so now how do I get potential at point I? Okay, so here let's pretend, let's say it's a question, very interesting one. So how do we really take this charge inside the shell? So let's pretend that we are really looking at small charges, and then let's say there is a tiny gap somewhere in the shell, and then we are able to take it inside. Okay, so how we are going to do that, we are not getting into that part. So let's say we are able to take that charge inside. Now once inside, okay, so if you recall the shell theorems, one of the shell theorems says that once inside, the electric field is 0. So that means if you move, let's say if you move around from one point to another, so let's say if you take 2 points inside the shell, so point x and point y, when you move a charge from x to y or y to x, whatever, there are no forces. Okay, so you're not working against anything. Okay, so in moving a charge inside the shell, work done is 0. So this is very important. Okay, so in moving around, okay, so moving around inside the shell, work done by external force or even by the electrostatic force is going to be 0. So work done is 0. So that means the change in potential is actually 0 inside. Okay, so the change in potential is 0 inside. So whatever potential that you have at this point S should be the potential at any point inside, because there is no work done. The potential should not change. So the potential at point I, for that matter, potential at the center, so anywhere inside, should be same as that at a point just outside the shell. Okay, so I think we are done here.